streaming on. Voice is good. I put on the extra mic too. So are there any questions about the homework assignment? No questions? First question is there a homework assignment? Yes, there exists a homework assignment.
There's at least one.
There's at least one, exactly. Or you can say it is not true that there's none, right? All right. So if there are no questions about the homework assignment, we are going to continue the discussion on counting. And let me turn the mic on, just in case the air circulation turns on again, which it might anytime. So did you guys have a nice Pi Day last week? Yeah. Last Thursday was Pi Day. Yep. Okay. Did anyone go to the STEM Center and watch our college president get pied?
Saw the aftermath.
You saw the aftermath. Okay. So I saw another professor coming out of it, and he walked by me and he said, "Did you see Dr. Green, our president, get pied?" And go like, "No." And then I paused and I go like, "That would be irrational, because pi is an irrational number." So he looked at me and then go like, "Tack, this is too much. You are too much."
Did you make it to your thing on time? Last, I believe it was last Wednesday.
Yes, I actually did. I went to downtown on time. I think I got there like 5 minutes before 2:02. So it's doable during that time, even though there's a little bit of a slowdown at about Cal Expo. So it's always a slowdown there, just because of all the merging. Yeah. So it was not bad. Could have been a lot worse. Yep. So, okay, so we'll go ahead and continue with our counting, and this time we are going to look at an example because it's a little bit abstract, the generator itself. So what we'll do is we are going to take a look at how it works. Okay, so I think last time we were looking at this mess here, and I was saying, okay, let's go ahead and look at omega 3 with omega 2 with 3 elements in a set. Okay, so I think that was what I said last time. Okay, so does anyone have a chance to work on this over the weekend? Like just kind of try to generate it. Okay, so how did it work?
It wasn't too bad. You just kept expanding it until you got a bunch of like tuples of tuples.
Yep. Well, you have a lot of set of tuples and stuff like that. Okay. All right, so that's what we'll do today. So I just want to bring up the slide so that people know, where we are at, okay, or what is the following exercise about. And then we'll go ahead and work on that using Zernal. So I can actually write, well, let's see, would it be faster for me? Nah, it will be slower for me to write it than to type it. So I'm going to type it instead. And as I'm typing it, some of you probably will be thinking, well, we can do it with a program, right? And the answer is absolutely yes. Okay, we could have done it with a program, but the program would not be very step-by-step. So we're going to do it step-by-step here. Okay, so ultimately what we want to do is to find out what is omega 2 of the following set. The set only has 3 elements. We'll just pick A, B, and C instead of numbers. So there we go. Okay, this is what we want to figure out. So you look this up and go like, okay, is this the easy case to solve? In other words, are we looking at omega 1? Why is omega 1 special? Because omega 1 is where the recursion ends. So when you look up here, omega 1, see this part here? If you are trying to figure out omega 1, then whatever set you're given with is the answer to itself. Now, technically speaking, it is not the case, because technically speaking, you end up with there's no easy way to actually generate that except to put everything into tuples. but that's basically what you end up with. Okay, so right here, we'll say that, well, okay, that is not the easy case because it's not omega 1. Instead, it is the general case, which is omega I. Okay, so we look at omega I here. This is an abstraction. Okay, so the first thing you notice is forget about the right-hand side because that's actually how we spell out the detail, right? So you look at the left-hand side. You ask, okay, how do we fit omega 2 of, in curly brace ABC into this format here? Well, I equals to 2, okay? And T is a set, which in our case is ABC. Is that okay? All right? So we are basically just specifying parameters into the left-hand side of this equality. So now we go switch back to here, and then, okay, so this 2 is basically what I is, and then ABC as a set is what T is. Okay, now that we understand what is I and what is T, what is it expanding to? This big U is a union of the following, okay? So it's the same thing as a sigma for summation. Okay, so you have to basically know, okay, what is our index variable? Because in a summation, we typically just have I going from 0 to R or something, going to some number. But in this case, we don't. In this case, our indexing variable is the lowercase e, which is an element of T. In other words, this is kind of like a for each loop. It's basically saying for each element E of T, do the following, okay? Whatever we do in the following gives me a set, and that set is going to be going into one big huge union. That's what the big U sign is saying. Okay, so it's saying for each element of T. Okay, so that means we have to look into T and then say we're doing some operation for each element of T. So switching back to here, the way I'm going to represent it initially is to say, okay, we do something with A, which is an element of T, right? And then we do something with B, and then we do something with C. I use the star slash notation. I'm hoping you guys know how to read that by now. Yes? It's just a weird context to use it, but nonetheless, it has the same meaning. It's just comments, okay? It is not a value. It is just commenting and go like, okay, whatever follows this has to do with element A, element B, and elements of C. Is that okay? Okay. All right. So now that we have spelled out, for what E are we talking about, now we focus on this side here. Okay. So for each row that I have written, the first row is when E equals to A, the second row is when E equals to B, and then the last row is when E equals to C. This is what we're doing. Okay. We are just saying, let's go ahead and compute the Cartesian product. Between what? Between the set of whatever element we have chosen for each row, and then omega I minus 1 of blah, blah, blah. Okay. So it looks nasty, but it's not really that bad, because we know what I is already. I is 2, I minus 1 is 1. So it's really just omega 1 here of whatever. Okay, what is that? T minus, T is a set. So we're looking at the difference between T and the set consisting only of the element that we want to focus on. So on the first row, it will be T minus A, which means, oh, it's the entire set T without A. That would just be B and C. On the second row, it will be A and C, and then on the last row, it's going to be A and B. Okay? So now that we know that, okay, let's go back and write that here. So I'm going to say in parentheses, because I want to group everything, right? So we have, the set of A by itself, Cartesian product with omega 1 of the set ABC, but without A, okay? Well, that means, we just have B and C here. Okay, that's 1. And of course, I could have just copy and pasted it. So this is omega of 1 again, but this time we're looking at T minus B, which means we only have A and C left. And then the last one is C Cartesian product with omega of 1, and then we only have A and B in this one. Are we doing okay so far? So now we have each individual term, okay? So switching back to the notes again, okay? So now we have generated all of these terms. There are 3 terms in this case. The next question then is, what are we doing with those terms? Well, that boils down to this operator here, okay? If we're doing a intersection, then we are intersecting all of those individual items. Since we're doing a union, we're just unioning all of those terms, okay? So I switch back to here, and I'll just spell out the word here, because there's no easy way to type. Well, I suppose I can use a big U here. Okay, there we go. Big U. All right. Oh, okay. That doesn't sound too bad, right? Because, I am just now defining omega 2 using omega 1. Is that part okay? Do we have any questions about what we have here in the notepad? Okay, if there are no questions, we continue, okay? Because now the next question is, oh, okay, what is omega 1 of omega 1 of BC? Well, that's an easy one, because according to the definition here, omega 1 of T is just T itself. Now you have to remember, we are not, T is, in this context, is no longer A, B, and C. It is just B and C now, okay? So because we are switching to look at only one term out of the 3. So omega 1 of BC is, okay, just to set BC, omega 1, I mean the rest are pretty boring because they're really the same thing, except we just have different elements in the set. Okay, the last one is AB, okay? So we just get AB. Okay, so now we can plug those back in, right? So when we plug it back in, now when you're copying on a piece of paper is not going to be nearly as convenient because you cannot do this. Nor this. So don't try to spend too much time doing the copying. Instead, focus on the concept, because I'm pretty sure the recorder is on. Okay, let me just double check, make sure that is the case. So the recorder is on, so that means your energy is better spent just by looking at and trying to understand the approach, because the mechanism itself is awfully boring once you understand it. So the question is, do we understand the concept? So are we doing okay so far? So the third stage is exactly like the first one, except I did a whole bunch of substitutions. So now let's go ahead and actually do the Cartesian products. So once again, this is something that I can do easily, but if you're using a piece of paper and pencil, it's not going to be that easy. Okay. All right. So we look at this Cartesian product and we go, oh, okay, it's just pairing A with B and C. Okay, we generate basically a set of 2 tuples where we have AB and AC, right? And then the second one is, oh, okay, we are just generating a set of 2 tuples where we have B starting, and then A is the second one, and then B starting with C as the second one, and then this one here is kind of the same thing, except we have A, B, and oops, I got it wrong, sorry. We got C, A, and then CB, like that. And somewhere I'm missing this curly brace. Alright, so are we good so far? So I'm just multiplying out, or I'm just carrying out the Cartesian product operator here to get me the actual set of 2 tuples. What do we do with all these 2 tuples? Oh, sorry? Union. Okay. So the thing about union is, if you know that these individual sets do not have any intersections, then you don't have to worry about a single thing. You just kind of lump everything together. Okay. The only time you have to kind of pay attention is, what if these individual sets, have intersections that are non-empty, right? There are common elements. Well, we know they cannot have common elements because everything on the first row starts with A, everything on the second row starts with B, and everything on the third row starts with C. And with tuples, ordering is important. Okay, so we know that they cannot have intersections or non-empty intersections. So that means the union is nothing more than just dissolving the boundary between each individual set. Okay, so we just get rid of all the extra stuff that we don't need, and even that can dissolve. Okay, and we can now dissolve that too. So we basically just end up with one large set of 6 tuples in this case, and that's it. That's the answer. Do we have any questions about the mechanism itself? I just chose T to only have 3 elements, and we are trying to find omega 2, but the approach is the same, when T is gigantic and you're trying to figure out 15 instead of SI. But the idea is the same. Are we doing okay with this? The general idea is okay? Cool. All right. Now these are permutations because we can see that AB is represented and BA is also represented in the set, which means AB and BA are considered different outcomes. Well, that's because ordering is important. How many people still remember the context of the Baskin-Robbins example on last Wednesday, and not just, oh, I want ice cream? Okay. Sorry?
I remember.
You remember, very good. So this is basically asking the question, okay, let's just say that, Baskin-Robbins has a deal, okay? And it says, if you order two 3 scoop, item, and they're identical, they give you a discount, okay? Because, they can just go like, okay, 2 employees can do work on exactly the same thing, and it's easy, okay? So now the question is, does it matter what order you specify the flavors? Okay, if you say, okay, vanilla, chocolate, and strawberry is considered different from strawberry, chocolate, and vanilla, then we're talking about permutations, like this. Okay, each one is a unique outcome of the experiment. On the other hand, if Baskin-Robbins says, well, as long as they're the same flavors, it will still be counted as the same, okay? Then we're talking about combinations. Well, this is not generating the set of all combinations. So there are several ways to look at combinations, and you can basically look at this and go like, we combine all of the tuples that have the same elements into one single set, okay? Then we have a set of sets, where each set is the inner set is representing a combination. So we can look at it that way. But there's another way to look at it. So the other way to look at it is a little bit more obscure, but I think mathematically this is also the other way to kind of generate it. So let's start with section 7 here. Occasionally, ordering is not important when the outcomes of an experiment is considered. In this case, an outcome can be considered a set. Lotto is the same thing, okay? When you buy a lotto ticket, the way you specify those numbers is not important. If you say, I want to choose 5, 4, 3, 2, 1 as my lucky number, it's no different from specifying 1, 2, 3, 4, 5, 1, 2, 3, 5, 4, or writing the numbers in a vertical way, okay? So that is a combination. So now the question is, how do I use an algorithm to generate all possible combinations, not permutations? We got permutations done already. All possible combinations, because I'm interested in that, okay? So the way to do that, this is a kind of long way to do it, but there's a, later on that we'll talk about a kind of shortcut to do it. So the long way to do it, okay, is first of all, we use a notation. Instead of using omega, I chose to use a big U. Okay, so U of I of X is representing the set of all possible combination outcomes of an experiment that has I trials. So the context of I, or the meaning of I, is the same as the big omega notation. It's the number of trials. And then X in this case is the same thing as the T before, which is the set of choices available to the first trial. Okay? Are we doing okay so far with the symbols? What they mean? Good? Okay. So what we do is we look at the first one, which is, there's only one single trial, which is easy to represent, right? So we're looking at one single trial, and you're given with a particular set X, which is what you can choose from for that one single trial, for an experiment that only has one trial. Is that okay? So in this case, the outcome is the union. Okay, once again, we use that notation. So we are iterating through every single element of X, but every time we encounter an element, we just say, make a set of its own, and then make another set around it. But that's because we have the union of all of these. So that the result of this is going to be a set of one element of X, a set of another element of X, a set of another element of X, and then everything is grouped in a set. Let's do an example. So we go back to the mouse pad, and we'll just do one quick example here. So we say U subscript of 1, okay, we only focus on subscript 1 here, of a set, okay, let's say AB, okay. So that becomes a set itself, A, B in its own set, and then each one is an element. Why do we do this? This seems like a waste of time. Well, it's not a waste of time because A in a set is representing the outcome of an experiment. The set of B is also representing the outcome of an experiment. This is why I said a little bit earlier, the way I did the omega one is kind of cheating because each one really should be in the tuple representation itself, but I chose kind of not to do that. Okay, so is this part okay? Are you guys all in agreement that if you have 31 flavors, okay? So in the case of Baskin Robbins, you'll be dealing with something like this. Oh, whoops, sorry. I just got it wrong here. So you have vanilla, chocolate, strawberry, bubble gum, blah, blah, blah. Like that. Okay. Because you have all of these flavors to choose from. But this is a one scoop. Okay? So now the question is, if you're only allowed to choose to have one scoop, okay, how many different one scoop possibilities can you have? 31, right? But when you look at this, okay, this is representing the one scoop, okay, the actual one scoop ice cream, serving that has vanilla as a flavor. This is representing the one scoop that has chocolate as a flavor, and so on. In other words, the set that you see on the left-hand side is what is available. Okay, that is representing all of those 1 gallon of whatever size of the container is that somebody's scooping from. Okay, that's this part here, the available flavors. On this side, each item in the set is representing an actual one scoop serving as a possibility. Yep.
The set within the set is always an outcome, right? It's one of the outcomes.
Well, before these are tuples, and now they are sets, because tuples are order dependent, and a set is not order dependent.
Right.
Yep. So are we still doing okay so far with this?
So in the case of U2 for combinations, you would still have sets and not tuples.
Yes. So we'll get to that part. Okay, but that's only with one scoop. The question is, what happens when we have multiple scoops, like I scoops? Okay? So when we have I scoops, it looks really nasty. It just looks, the notation looks kind of like that. But we'll take a look, okay? Because we got double loop here. The outer loop is saying, Well, let's look at the element, each element of x, which is coming from here. Okay, so it is kind of the same as before. This what we have inside here is a little bit nasty because what it's looking at is we'll pick out something from ui minus 1 x minus e. Okay, we'll pick one element out of it, but each element out of this ui minus 1 notation is a set on its own. So uppercase S is a set, and then we will form a new element, which is a set on its own, and it is the union between a singleton set of E and whatever S is that we have chosen from U of subscript I minus 1 x minus E. So it just looks really nasty. So let's go ahead and work on this one. Is that okay? All right? Okay. So what we'll do is we'll continue our obsession with ice cream. So this time we'll say we're looking at 2 scoops, okay? Give me all the way to have 2 scoops where order is not important. And we are looking at, I want to do something that's easy to write. Okay, vanilla, chocolate, and strawberry. Is that okay? All right. Okay, so now we say, oh, okay, we got 3 rows. Okay, how do we get the 3 rows? We got the 3 rows because of this part here. For each element of x, do something, blah, blah, blah. Okay, so we'll have those 3 rows. Okay. So once again, on the first row, we're dealing with vanilla. On the second row, we are dealing with chocolate. And on the third row, we're dealing with strawberry. Okay. Is that okay? So are there any questions about there are 3 terms on the outermost part of the union operator? Okay. So now we look at each one and go like, what does it look like? Okay. So for each one, this one looks like, so we have to pick, okay, so the first thing we need to do is to figure out what is u subscript I minus 1 of, oops, I'll just say 1 because that's, because I is 2, I minus 1 is 1. Is that okay? So it's u1 of x minus e. Well, x is VCS, right? And we all know that E is V. Oh, I messed up the notation. Okay, I have to correct this. I messed up the notation because you cannot have an x minus E. You can only have an x minus the set of E. E is an element. You cannot subtract an element from another set. You can only subtract a set from another set. So I messed up here. I'm going to fix it first. This is module 0305. Okay, let me go fix it. This is the power server. I certainly don't want to do anything on the power server for this. I was using a lot of virtual machines one time in teaching classes. And so whenever I finish using a virtual machine, I use power off, to turn off to properly shut down the virtual machine. And there was one time I was actually on the power server, and I thought I was on a local virtual machine that I only use for teaching. So I said, well, I'm done using it. Let's turn it off, power off. Well, that turned out to be the actual power server, and it was, I think it was 8 p.m. or 9 p.m. There were no one over at the lab that could help me restart the power server because I do not have access to the console to the virtual machine, which I needed in order to restart the server. I think it was on a Friday too, so I had to call Walter in and get it done. It was interesting. So I learned to look at my command prompt before doing something like that. 0305. And this is like toward the end. Yep, there we go. X minus E Well, the curly braces is there, but I need to backslash it. Because in LaTeX, curly braces by themselves are only used as a grouping. Okay? So it's basically just saying, oh, we'll group E by itself. It's a useless group. But in order to display the curly brace, it needs to be escaped with a backslash. So I forgot to backslash it. That's why it looked right when I look at the text document, but it doesn't look right when it's generated. Okay. So we just have to republish it. And go back to my browser. Update. And I believe it is okay now. Yep, there you go. So I do apologize for this mistake. And now we can move on. Okay. So now that we have the right notation, we can kind of move on to here. It's not really critical, you know, because I think from context, we kind of know what it means. But nonetheless, you know, it is it's a type mismatch, basically. All right. So what is U underscore 1 or U subscript 1 on the first row? Well, it would be the whole set, but without the V. Is that okay? Because it's the whole set minus the set with only V in it. So that means, you know, we only got chocolate and strawberry left, which is the second trial of the experiment. Is that okay? So let me say that one more time. The first row is representing what if we choose to use vanilla in the first trial? Then what is available in the second trial? Well, if we have chosen vanilla already, then we only got chocolate and strawberry left as choices for the second trial. That's why we have the subtraction of the set that has, you know, whatever element we're focusing on with this particular set. Okay? All right. And we can't really do much after we figure that out. So we'll go ahead and just say that on the second row, we have to figure out U1 of VS. And then on the last row, we'll try to figure out U1 of the set without S, so that would just be VC left here. Okay, so we'll go back and do something later on, because right now we had to figure out, you know, U1 of those three things first. But U1 is easy, okay? So I'll type this first, and then we'll switch back to the definition of U1. So when you switch back, okay, I can try to position things just like last time. Get this all the way close to, all the way to the bottom. There we, oh, but we're looking at U1. There we go. Okay, so when we look at the definition of U1, oh, it really is just listing every element as a set on its own inside a bigger set. Okay. So U1 of CS is the set of C and the set of S. That's it. Are we okay at this point? This is really important. It doesn't seem to be very important. It's like, okay, we're just adding parentheses around everything. And obviously in C and C++, it doesn't do a single thing, because you're just making a block statement out of a single statement, which is still doing the same thing. But in the context of a set, you know, related topic, it does make a big difference. Because originally we have a set of flavors. Now we have a set of sets of flavors. Is that okay? We are switching from available flavors, okay, in those, you know, 1 gallon, you know, tubs, to actual, you know, 1 scoop on a particular cone. Is that okay? All right. So the other two are kind of the same thing, okay? U1 of, the next one is what? VS. It's kind of the same thing, okay? Nothing really too bad here. And then we have the last one. It is VC. Like that. So are we good so far? Good. Okay. So now we go do a substitution back to U2 here, because we have just figured out, what those sets are. Okay. Okay. So once we switch back, let me just scroll the bottom part a little bit, so that we can now pay attention to UI of X. Okay. Scroll up a little bit more. There we go. All right. So now we know what this thing is. Okay. And now we can just say, okay, what are we doing for each row? Well, we're doing something with each element of U1 of something, okay? So now we know what U1 of CS is, okay? So we're basically saying we're doing something with C, we're doing something with S, and then we're doing something, that's it, on the first row. And then on the second row, this is not doing any actual set operations yet. I'm just spelling out what we're doing something with. So on the second row, it's going to be the set of V, the set of S, and then on the third row is the set of V and the set of C. Okay. Because we have a double loop. Okay. So with a double loop, the outer loop generates each iteration of the outer loop is one row. Okay, or one line, and then each iteration of the inner loop is each item inside the parentheses. That is how I'm organizing, the display of all this stuff here. Are we good so far? Okay. So now we look at each one and go like, oh, okay, we're supposed. So what we have here, this is S. This is one case of uppercase S. This is another case of uppercase S. Okay, so now we need to look at this and go like, okay, so we are supposed to do a union between E. So E is already chosen on the first row as V. Okay, and we say union that becomes a set on its own, and we are going to union that with V again, union with just S as a set, like that. Are we doing okay with the transition? So let's do it on the second row. What you're looking at here, okay, the set of V, the set of S, these two are elements of U1 of VCS minus C. Yep.
If you union it like that, won't you have like the set containing the set containing VS?
We'll see. We will see. Okay, so this is corresponding to one choice, to one thing we can choose in U1 of this thing here. But we have to union it with E, or the set only consisting of E. On the second row, E is C. So that's why we are now looking at C union with this, and then we have a union with C again, union with S, like so. And then the third row has E being S. Okay, so we have S union V, and then this whole thing union with S union with C, like so. And we know what to do to join all the different rows, because they're all supposed to be unioned with each other, like so. So are we still doing okay so far? Okay. So let's go ahead and try to figure out what this is going to give us. Okay. We'll do it step by step. So I'm going to get rid of the comments here, because that really is not really needed anymore. So this just gives us a set of VC, right? And this just gives us a set of VS. And by unioning these two, okay, they're different. So we can, in this case, we can just dissolve this, and we're done with the first row. Are we good so far? Okay. On the second row, kind of the same deal, okay, because the pattern is the same on each row. So by union C as a set, V as a set, they're not the same. So after you union, it becomes one larger set, which has C and V both as elements. Yes?
So you do get that like set containing the set, the outer
Yes.
union smushes
which is needed, which is
Okay.
important. Yep.
That makes sense.
Okay, and then we can do the same thing over here. We look at the element C and the element S, because when you look at a set that only has C and a set that only has S, these two do not have any overlap. Their intersection is empty. So when you perform the union, it would be a bigger set that has both C and S as elements, just like kind of what we did before. So we can dissolve the boundary between those two sets. And then we look at the set that only has one element CV, and we look at the set that only has one element, which is the set of CS. They are different, okay? So now we can dissolve these two and go like, okay, we just make a bigger set out of the whole thing. Last row, same thing, same deal. Now, if you do have any questions, this would be a good time to ask and clarify how we can dissolve the boundary of these sets by using the union operator. Do we have any questions? Because if we have any questions, about the concept of what is a set, what union actually does to a set, to two different sets, this would be a good time to ask. No questions? Yes?
So it's like the only difference between this and the one we just did, the fact that instead of Cartesian product, you have a nested union and you replace
Yep.
your...
Yep, exactly. Okay, so now what do we do? Well, we have to perform the outer union operations. Now this time we have to be careful because there are overlaps. So we are looking at a set that has two elements. One element is VC, one element is VS. Those are sets. And then we are now looking at the second row, which has a set that has an element which is a set CV and another set which is CS as an element. Then we go like, oh, well, the union is a little bit tricky because I can't really just dissolve these boundaries, okay? Let's see what happens when we dissolve that, okay? We end up with something like this. But there's a problem here because one thing about a set is an element can only occur once. And now we are seeing one element occurring twice because the set VC and the set CV are exactly the same because ordering is not important inside a set. Choose one, doesn't matter which one, okay? Just pick one, okay? So let's just say that we pick the first one. So we have to erase the second one because it's a duplicate. Now we look at the dissolving of the set boundary between these two and go like, do we have a problem here? Yeah, we have a problem here because VS and CS SV are the same. In other words, this set as an element is really the same thing as this set as an element. So we can only keep one of them, okay? Doesn't matter which one you keep, okay? You can keep the first one, you keep the second one. I'm just going to erase the second one. And now we also have a problem because the set CS and the set SC are really the same. Pick one to delete, okay? We'll delete the second one. So after all of the deletion of the duplicates, we end up with just that. In other words, if you have 3 flavors to put onto a 2-scoop, ice cream cone, okay, you can only have 3 possible ways when ordering is not important. Are we doing okay so far with this? Yes? Okay. So someone is going to be smart and say, oh, but we can do all of this without all of these, really tricky set operations, because we can sort the flavors, okay? And then we just say that, when we list items inside a tuple, we can keep tuples as long as they're sorted, okay? Well, that is great if the elements in the set of choices are totally ordered. But what if they are partially ordered, or they're not even partially ordered? Then you cannot order them. And if you cannot order them, that concept that I just talked about and go like, okay, let me give you another example. Let's say we can choose from 1, 2, and 3, okay? Choose any 2 out of 1, 2, and 3. So one way to quickly generate all the possible combinations is to say, let's see if I choose 1, what can be the second item? 2 or 3. Good, okay? I choose 2 as the first item. What can be the next item? Only 3. Why? Because I don't want 2, 1 reappearing. So if you can sort the elements representing what choices you have, then you can use that trick by using the sorting approach, okay, which is a very quick and easy way to generate possible combinations. But on the other hand, if that set is not ordered in any way, okay, then you cannot use the sorting concept. So this approach works for every single set that you can choose from, not only set of items where total order where they are totally ordered. Is that okay? Because I just want to kind of give you guys an idea of, oh, if you're dealing with things that are sorted, it can be a lot easier. But if not, then you have to resort to this. So are we good so far with all of this stuff? Okay. Okay, let me ask those people who played the Mastermind game after my introduction of that game to the class. So, so I know a few people play that board game. So what do you think of that board game? Is it difficult to play, or is it kind of like, eh?
It's fun. It's cool. I like it.
You like it? Okay.
Yeah, I played like maybe 5 times, and out of 5, 3 times I guessed correctly.
Okay.
The first 2 I was learning how.
Yep. Well, you got to play a few times to learn the rules and also to figure out how to play it. Yep.
Yeah, I remember I played it. I think on my second time I guessed it.
Uh-huh.
The first time, like, the person I was playing with messed up was actually not following the rules.
Okay.
But yeah, it was I could see it getting tedious after a while.
It can get very tedious because it's all about the elimination of possibilities. Okay. So in that particular game, we're dealing with permutations. Well, it's a little bit more worse than permutations, but we are looking at because you can have colors reappearing. The question is, how well can you track the remaining possibilities? Now, human mind, can do it up to a certain degree, but once you have like 6 different peg positions, and let's say 10 different colors, it becomes very hard for a human brain to process it, because the process of elimination basically is just like, okay, so think about it this way: we have 10 different colors, okay, and then each position can be any one of the 10 colors, and it is with replacement. How many total possible outcomes are we talking about? Ordering is important, by the way. So imagine this in your head. You got 6 positions,
Just 10
okay?
times.
It'll be 10 to the power of 6, which we conveniently call a million, right? So there are a million, right? Yeah. So there are 1 million possible outcomes, okay? And then whenever you guess, okay, you say, is it this? You get a score, okay? That will help you eliminate some of the possibilities because it wouldn't be consistent with that particular outcome, with that particular, I shouldn't say outcome, with that particular score. Okay? But what is remaining? Can you track that quickly in your head? The answer is no. Okay, so after 2 or 3 scores, I mean, obviously your choices would be kind of whittled down quite a bit. The question is, well, out of 1 million, maybe it whittled down to 4,000 or something. Okay, do you know what those 4,000 remaining possibilities are? Not easily. Okay, so that's why there are certain things from a programming perspective. It's like, yeah, we can do it, but from the perspective of, can you do it by hand? Yeah, we can do it, but only up to a certain point, because beyond that certain point, it becomes very difficult for the human mind to keep track of what is still possible. Is that kind of making sense? But that is the reason why we kind of want to have these generators, because without the generators, we cannot keep track of, what is left, what is available, what else can I choose from. Are we doing okay with those concepts? Like, when do we actually apply these functions or generators? Okay, very good. 1 million possibilities. Isn't that a lot? I mean, can we really track all of those, in a computer? How much RAM do you have? I mean, even the worst laptop computer these days have what, 4 gigs of RAM, right? How many bits do you need to represent each possible combination, each possible outcome? So it depends on how you encode it. Okay, so let's visit that just a little bit, just a little bit. You got 1 million possible outcomes in this particular experiment. Okay, so once again, let me repeat the experiment. You have an experiment of 6 trials, where each trial has 10 choices, and this is with replacement. Is that okay? And that's why we end up with 1 million possible outcomes. Okay? The question is, if you code it correctly, how many bits do you need in order to represent a set in this case?
Just use a bit for every element.
Hmm?
You just use a bit for every element.
You just use 1 bit for every element, so you need 1 million bits, right?
Makes sense.
You need 1 million bits, where a 1 for a bit means this is still possible, and a 0 for a bit means it is no longer possible. Okay, so assuming you don't even bother with like zipping or using some other compression algorithm, because at some point you can end up with a lot of runs of zeros, which means you can further compress it by using just run length limit, okay, RLL. But assuming you don't even bother with that, okay, and those bits are all over the place, so run length limit is not buying you anything, okay. 1 million bits is how many bytes?
1 megabyte.
Huh?
That's divided by 8.
Yeah, divided by 8. Very good. What is 1 million divided by 8? 125,000. Okay, 125 kilobytes is what you need. Do you think you can spare 125 kilobytes on your computer to store a certain kind of data structure?
It's possible.
It's easy peasy, right? So that's why I said it's easy to do, but in the good old days it's not so easy to do. Okay, when I say good old days, let's just roll back time let's go back to the 1980. Okay, so 1980 is, I think, when the Apple II computer first came out. So let me just look up when the Apple II computer was. Apple II 1977. Okay, so the Apple II computer came out in 1977, and I think the first revision of these computers only came with 16 kilobytes of RAM. So it would be impossible to do it on a computer like this. Okay, now I shouldn't say totally impossible. It would not be able to keep track of the set of which outcome is still possible. It would have to regenerate everything from the beginning, and then just rule out the ones that cannot possibly be the case on the run, okay, which is highly inefficient because you basically have to redo everything over and over and over again. So it will still be able to, if you code it correctly, it will still be able to do it, but will be much slower compared to a modern computer. So why do I bring this up? Why do you think this is important? How many years how many years is between 1977 and 2019? 42 years. Okay, approximately 42 years. So 42 years sounds like a long time. Okay, but it really is not. Okay, I think I have talked about this multiple times in various classes. If you take a car, okay, automobile, okay, from 1977 and you compare it to the same kind of car today, you do not see the same kind of advances that you see with computers. Okay, what kind of changes are we talking about in terms of processing power? Well, it doesn't say here, so it says a little bit, the CPU is a MOS technology 6502 processor. What is that processor, 6502? It's an 8-bit processor, for one, okay? And what is how many bits, or what is the width of the calculation of your modern day i3, i5, i7 processors? 64 bits, okay? So if you want to perform 64-bit calculations with this processor, it will take at least 8 times as long, even if everything else is the same, okay? That's the first thing. Second thing, how many clocks do you need in order to compute the addition of 2 integers on a modern day processor? 1 clock, okay? And that's due to pipelining and a whole lot of other tricks. On this processor, not so much, okay? Even for just adding, it's gonna take a few cycles, a few clocks. Let's say I'm optimistic, let's say 5 clocks, okay? So now you have another 500 factor, of your change of magnitude. Clock speed, what is the basic clock speed of a processor, okay? So with a middle end type of i5 processor today, okay, using the latest Intel technology, what is the clock speed without not counting turbo? 2.4 gigahertz, right? This is 1 megahertz. Okay, doesn't that tell you something? Okay, because to some people, it doesn't seem like a whole lot. Okay, so 1 M versus 2 G. Okay, whatever. Sounds like about 2 times. No, we're talking about 2,000 something times just for clock speed. Okay, so the amount, how much RAM does it have? I just said it, right? 16 kilobytes of RAM. That's when it first came out. The last version had about 32 or 64 kilobytes. Okay, and if you go to Fry's right now and buy a middle of the end type of middle of the road kind of computer, like a desktop, how much RAM do you think it usually comes with? 16. Do they still sell 8 gigabyte computer?
Yes, but I don't think you could find like 16 kilobytes of RAM anywhere. I don't think you could find that, like anything under like.
So let's say it's 16 versus 16, okay? So you're talking about 16 gig, right? 16 gigs or 16 billion versus 16,000, okay? So that's another huge order of magnitude change in terms of storage capacity. This is not even counting the hard drive. This thing has no hard drive. What if you want to store something persistently? Get your cassette tape out. And I'm not kidding. It can store information onto a cassette tape. So you can plug in a normal cassette tape player. Okay? If I teach this class 5 years from now, people will be asking, what is a cassette tape player? That's the kind of thing that we do before CD players. What is a CD player? Because people are just going like, oh, what do you mean by you don't know what a CD is? How do you get your music? App. That day will come soon because things are going faster and faster and faster. The pace is going to be increasing faster and faster. So we are talking about something that was not possible with this computer, but today it's like, yeah, we can do this. If you give me the algorithm, I have plenty of processing resources to solve that particular problem. But why is that important? I mean, it's in a class like this, especially.
Is it going to relate back to security?
Huh?
Is it going to relate back to security again?
We talked about security, but the whole idea is you can have an algorithm that was impractical, useless, in the past because we just did not have the processing resources to do it. So it becomes just a theory. It's like back in 1977, somebody came up with an algorithm and say, yeah, in theory we can solve this problem. And then they look at every single computer on the planet and go like, even if we combine every single computer on the planet, we still don't have resources to do it. So yes, in theory it's a great idea, but in practice it is useless. And then today, we look at the same algorithm, and people can say like, oh, I can use my Fitbit to do it. My Fitbit has more processing power than what is needed to do this, to solve this problem. But why is that important? So if you roll the time and you come up with a theory today, and you say, oh, if we combine all the processing resources on the planet today, we cannot solve this problem. It is a useless theoretical exercise.
Just wait.
And you
Wait
wait
like
even
10 years.
less now, right? Because
Yeah.
your progress goes faster and faster and faster. So in less than another 42 years, that problem may be solvable because the computers at that time, like within 40 years, will have the resources to do it. Okay? But then why is that important? It still doesn't answer the question. Why is it important? We are doing a lot of projections. We are talking about a lot of possibilities. But why is this important when you want to become a computer scientist as opposed to a software engineer? What is the difference between a computer scientist and a software engineer? What software developer? What is the difference? What does a computer scientist do? Hmm?
Solves problems.
They solve problems. They invent algorithms. They investigate properties of algorithms and solutions of algorithms. They investigate computational hardware. They investigate mechanisms of computations and so on and so forth. So those are the computer scientists. And then a software engineer would be someone who designs software. Okay, maybe at a higher level, maybe at a coding level, the line by line level, but nonetheless, using existing hardware, existing programming tools to write programs. So that's the difference. But what I just said means that computer scientists now actually have a lot more to do, because the boundary or the envelope of what we can do with computers is going to expand faster and faster and faster. So in the past, maybe someone can come up with a theory and then it won't be useful in 30 years. Today, maybe someone can come up with a theory that's useless today, but it becomes useful in just 10 years. So that gap is getting shorter and shorter and shorter, especially with quantum computing. So if anyone wants to kind of really keep an eye on the future of computer science, quantum computing is definitely one important item to look at. They actually made a time machine out of a quantum computer, so they could go back in time. Did you guys know about that?
I thought they could only do like some
Yes. But nonetheless, it's still cool.
but I mean, you gotta start somewhere.
Yep. Quantum time travel the TARDIS and the Avengers. No, we are talking about an actual experiment. I think it's not this one. Okay, when I find it, I'll send it to you. It's not terribly related to this class. All right. So are we okay so far with those concepts? Okay. I mean, the rainbow table is another thing that was kind of interesting. Does anyone know what the rainbow table is?
Just a table full of hashes like pre-computed.
Yep. That was not possible in 1977 for sure. So MD5 hash is pretty darn safe. It's not safe anymore. And people say SHA-2 is pretty safe now, but just give it time, it won't be safe anymore. So those items are kind of important.
What are those things that you just mentioned?
Oh, okay. So since you asked, hash MD5 rainbow table. There we go. Okay. And I'm just gonna look up the description of it. Okay, so a rainbow table is a pre-computed table for reversing cryptographic hash functions. MD5 is one of the commonly used cryptographic hash function. So the way it works is you can type a password, which is basically a string. Okay, they convert a string into an MD5 hash, which is a fairly, at the time it was a long bit sequence, but now today it's actually considered pretty short bit sequence. So your password stored on the computer is actually really just an MD5 hash, which is a bunch of bits. Okay. So the way your computer knows whether to let you in or not is when you type your name, username, it looks up the role, and then when you type your password, the password that you just typed in is now going through the same hash function. So if the hash value matches what is stored, then you're allowed to sign into the system. So this way, they never store the actual plain text version of the password, which would be like very, very bad. Okay. So this used to be considered a fairly safe way to do things, but that's not true anymore. Safe means in case someone can crack into a server and get the quote-unquote password, which is already hashed, it would still be, they still cannot get to the actual original password of the user. So that used to be considered fairly safe by using the MD5 hash, but that is not true anymore because of rainbow tables. So a rainbow table is a pre-computed table for reversing hash functions. In other words, you give it a hash value, it will give you a string that can generate that specific hash value. So if you have access to the password file on the server, okay, then you can go through this table and know how to sign in as each individual user on the system. So MD5 hash is no longer considered safe because of that. Now I did mention something about SHA2, SHA-2. So SHA-2 is a successful successor of SHA-1, and I think SHA are the initials of the people who came up with that algorithm. I could be wrong, but it's a hash function that gives you a longer string, which means if you were to generate a rainbow table, it would be much larger, quote unquote, so large that it is not practical or it is impossible for anyone to store. But once again, that's using today's technology. So in a few years, that may not be possible anymore. That is alarming. Back. I'll just go somewhere safe. Oh, okay. I take it back. It is just a secure hash algorithm. I hate terms like that because it is now secure. It won't be secure anymore in a few years. So it will still be called SHA-2 in a few years, even though it's no longer secure.
Yeah, we'll have SHA-3.
Then we'll have SHA-256. I mean, they already have SHA-256. And SHA-512. So,
We'll have Shaw gigabit.
Later on, they'll just name it the sloppy hash algorithm.
Slow change secure the sloppy.
Yep, some of these are already insecure. So SHA-3. So if you're interested in this, you can read it. It's really kind of interesting. They're all very interesting stuff, and everything connects to everything too. So, all right. So we are now done with counting. The next one that we want to look at are events. Okay, this one is a pretty short module. It's really just a definition of terms. That's not my notes. Okay, this is discrete probability. This is actually my notes. And let's see. And I did my own explanation of what an event is. So we'll just kind of use the rest of the time for today to kind of look at these terms. We talked about the birthday problem already, but I'm going to do it again, just so that we can use those specific terms. So a set of outcomes of so we know what a trial is. Okay, a trial is basically just an event, not event. Okay, take that back. So a trial is doing something that has a certain number of possible outcomes. Okay, so a trial has outcomes, but we can also perform experiments. An experiment is basically the repetition of trials. So you can say, I'm going to flipping a coin is a trial. I'm going to flip it 5 times. So that becomes an experiment. And experiments also have its own outcomes. So that's what we explored earlier in today's lecture. The set of all possible outcome is typically called omega, and that's why we chose to use omega I as the name of the function. An event, on the other hand, is a subset of omega. In other words, other than that, there's nothing really special about an event. Okay, so let me just say that one more time. An event is nothing more than just a subset. Doesn't even have to be a proper subset. It can be just a subset of the outcome set of an experiment. So what is the meaning of an event? Well, as it turns out, it's just that something that you're interested in. That's all. Okay? It's basically the subset of all the possible outcomes of an experiment that you're interested in. Is that okay? So I'll give you an example. Back to Baskin-Robbins. Okay? So let's just say that you are you really like chocolate, and you like how chocolate and lime kind of combine. Okay? So now your question is, out of all the possible ways to have 3 scoops of chocolate on a cone, okay, and let's say Baskin-Robbins has a is this your lucky day event? Okay, so for half the price of a regular cone, they'll just randomly slap something together and give it to you. Okay. So now you're interested in what are the chances that they will slap something together that has lime and chocolate on it. Is that okay? So all of those cone configurations, permutations, that has lime and chocolate in it becomes your event. It is a subset of all the possible ways to arrange 3 flavors in a cone, on a cone, but the subset is what you're interested in. What are the chances that I will get something that I'm actually going to like?
Could you say it's the same question if I want to know how many flushes there are in a type of person?
How many? Yes. Yep. Then you have to define what a flush is, and then you'll figure out how to define that subset. Yeah. So is that okay? What an event is? Yep.
The event should only have elements that you're interested in.
That is of interest to you. Yes. So E. Okay. So we typically use E to represent the set of event or the event that you are interested in. So when you look at the cardinality of E and divide it by the cardinality of omega, that becomes the probability of getting something that is of interest to you, assuming the distribution is even or uniform across the entire omega. So that is a fairly it's an assumption, but sometimes it may not be true. Okay? Why is it not true? Well, maybe lime and chocolate are really, really far away, around the corner of the counter. So the chances of, someone actually going there to scoop, chocolate or scoop, lime may be lower. So this is based on even probability. Okay, everything has the same chance of happening.
So there's always like replacement, like
It doesn't even have to do with replacement or not, because if you look at Baskin-Robbins, maybe there is a distribution across the 31 flavors that is not even. Okay, so this doesn't take that into consideration. It is assuming the chances of grabbing one of the 31 flavors is the same across all flavors. So we kind of have to keep that in mind of what assumption we have made when we deal with these math. So the next section here is to revisit. Okay, to us is a revisit because we talked about it already. So what are the chances that at least 2 people in the class share the same birthday? Okay, which is basically the reverse of asking the chances of everyone has a unique birthday. Okay. So now we need to define E. So in this case, E is so it's not defined here because I think in the end we want to define the flip side of E, not E itself. So a trial in this case is the birthday of a specific person in class. Okay, because basically we are looking at something like, okay, let's form a line for the entire class, and each person pick one day out of a box. Okay, that's kind of what we're looking at. And then we have n trials. N is representing the number of students in the class. And then we want to, the outcome is a single instance of an experiment of a class of 3 students may look like the following. In other words, if I look at a class of only 3 people, then we may have 2, 61, and 4, and those are the days in a year. Yep.
So in this specific case, we're not actually looking at the event E, we're looking at omega minus E.
Correct.
So
Because it's easier to figure that out as opposed to E
in
itself.
this case would be the set where everyone has different birthdays.
Correct.
Okay.
Or the way we process that in the past was to focus on that. So that becomes what is of interest to us. Okay. So the E for 3 people, okay, is going to look like this. This includes all the ways to have birthdays where at least 2 students share the same birthday. So this is not reversing it yet. This is actually looking at all the instances where at least 2 people of the class share the same birthday. So we are looking at 111, which means that all 3 students pick the first day of the year. 112, the first 2 students pick the first day of the year. The third students pick the second day of the year, and so on. So it is very difficult to emulate this and also to analyze and count this one. But the reverse is easy. So the rest of this, is basically coming to the same conclusion that we have already talked about. So instead of looking at it this way, we're looking at it in the opposite way. And we are basically forming the question slightly differently. We're asking, how many ways can we arrange birthdays in a class of n people where each person has a unique birthday? Okay? So the rest of this is just reasoning out the whole thing, based on what we have already talked about. Okay? And we end up with this number divided by the cardinality of omega. But because this E is really not what we are interested in, so we have to, excuse me, I take it back. F is representing the set of all different ways, but each person has a different birthday. So we have to take omega and subtract F, the cardinality of F from omega, to get us what we want. So that's why it becomes this equation here. So this is the actual probability of what are the chances that at least 2 people in a class of n have the same birthday. Is that okay? And as we already know, using a spreadsheet, that number is deceptive. Okay, in other words, with only like 50 people in class, the chances of at least 2 people in class sharing the same birthday is actually really high. Surprisingly high. So are we good with this section here? Okay, we are just revisiting the same a problem that we have seen already. So the next one is a coin toss problem. So with a coin toss problem, it's kind of interesting because it relates to gambling. And why do you think it's interesting when it relates to gambling?
It relates to money.
Because it relates to money. Very good. Because people want to know the chances of things, right? So when you walk into a casino, okay, what do you want to do?
Walk out.
Drunk.
Huh? Get drunk. So what activity will involve the least likelihood of losing money?
Leaving.
Leaving.
I'm told. Leaving.
Crap?
Craps, I'm told.
Craps. Huh. I did not know that. I always thought slot machines is a pretty safe bet, especially those that take pennies, because it's limited by how fast you can put pennies into the machines. So you have that you have that limiting factor.
Are there any that accept pennies?
I do not know.
Are,
Penny
but
slots.
you're not gonna get paid out at all if you win.
Yeah, but you can only put pennies in at a certain rate. So that's the maximum loss rate, right?
They have ones that'll take your credit card straight in now.
Oh,
Yeah.
that is
You
bad.
can't.
That is bad. Personally, for me, to spend the least money at a casino, but not by doing absolutely nothing, would be to beat the arcade center, especially with an old style Street Fighter. I can usually beat the kids. The kid would walk up to me like, "I can challenge you." Really? Yeah, that usually I can last 1/4 will last me like 45 minutes. So I consider that a pretty safe bet. And even if I get beaten, it will still take X amount of time for a kid to beat me, right? It's not like instantaneous. So, but anyway, so the importance of understanding coin toss partially has to do with gambling, but partially has to do with something else. Zeros and ones, right? Head is 1, tail is 0. Okay, why is that important? Because when you're transmitting data, those are all zeros and ones. So what does that have anything to do with gambling? Well, has anyone tried to do Bluetooth or something over Wi-Fi, like the old 2.4 gigahertz Wi-Fi, and somebody else is using the microwave? Okay, so we do have some experience with that. Well, the problem is, the microwave operates at about the same frequency. So despite all the shielding and all kinds of stuff like that, it still leaks out a lot of microwave frequency energy, which is going to interfere with your Wi-Fi operation. Okay. So now the question is, are you going to receive that 0 as a 1? Because it's now received erroneously. That is a coin toss, okay, with a certain probability. So your assignment over this weekend is to read over this. Okay, actually, today is Monday. Okay, so your assignment before Wednesday is to read ahead of me and basically try to read all the way to the end of this module, which we'll talk about binomial distribution and stuff like that.